Thanks a lot. So thank you for introduction, and thank you for inviting me here to speak to you about our efforts both in Meta and Oxford to build a foundation, the foundation for AI. So first of all, I'd like to explain myself a bit and set out the stage for the rest of the presentation. So what do I mean 3D foundation of AI? So if you look at this, oops, that was supposed to happen. So if you look at the slides, that's an image that I took from Vision, which is a book by David Marr from 1982. This is really the beginning of our discipline, if you like. And if you want to open up his book, maybe page 3 or 4, you find this. So obviously this is a code to 3D and 3D interpretation of data. So at the time, the belief was that in order to do any interesting computer vision, any interesting interpretation of images, the first step would have been to take an image, which is a 3D projection of the 3D world, and reconstructing that image into having a mental model of the 3D structure that you see with your eyes. And this was thought to be propedeutic to actually be able to do any interesting image processing on top of that. But if you fast forward 20 years later, actually things pan out in a very different way. So to the left here, what you see is a representation of illustration of black visual birds. It was a model which was introduced at the beginning of the century. The idea there was to just decompose an image into 2D patches and put those into a classifier. At the time, it wasn't a deep network, it was a superconducting machine. And that would allow you to solve tasks like, for example, image classification. All right? So here, there is no 3D per se. The image is seen as 2D pattern. It's fed into a machine, which is learned, superconducting machine, and then you get your answer. To the right, you see what happened 20 years later after that. That's a transformer. Same story. So you take an image, you decompose that into patches. Now, the machine that you put on top of that is much more complex. It's a transformer. It's not a superconducting machine anymore. But still, the image is seen as a two-dimensional entity. And with that, you can do great things. Certainly, you can do image interpretation very well. But there's no explicit 3D there. So why do we need 3D? And why I'm trying to promote the idea that it would be very good to have 3D as a foundation of AI and machine intelligence. Well, I think to me the main answer to that is that this is propedeutic to spatial intelligence. Well, spatial intelligence is a bit of a buzzword, but to me what spatial intelligence means is the ability of solving problems that require or entail a high degree of understanding of spatial phenomena. Okay? So what would be an example of a problem like that? I guess the most obvious one is robotics. So if you're a robot that looks at the world, has to interact with it, again, the world is two-dimensional. For the robot, though, it has a physical body. So it is very important to be able to parse this 2D world that it sees through images into a three-dimensional interpretation, for example, to be able to grab an object. But it's not just that. It's not just robotics. Suppose you want now to have a machine that is able to design this building, okay? In other words, suppose you want to have a machine that is able to solve engineering problems that concern physical systems. It could be structures, it could be mechanical engineering, all right? And now suppose you want to have ChatGPT that doesn't write code for you, but designs a building. Again, you need this machine to have a deep understanding of the dimensional structure and space. And I don't think you can get that from text alone, or for images alone. You really need to develop specialized skills in the manipulation of three-dimensional information. So this is what my research is about, by and large. And yet, this is not just because of, say, robotics or physical engineering. Everything in computer vision can be helped if you have a three-dimensional foundation on which to build. For example, consider representative data. So what you see here is a person preparing a meal, and this is captured from a headset, which is mounted on the head of the person doing the meal. And if you look at this data, it's actually very confusing. So it moves very fast, but also most of the motion you see there is not interesting motion. That's just the camera which is moving around. The interesting motion, which is actually the person acting in the scene, well, that's not really so visible because it's drowned into the motion of the camera. The other point you see here is that you have this sort of tunnel vision. So you see at any given point in time only what is immediately in front of your eyes. But of course, this action is happening into a world, right? And this makes sense only if you can consider the world in which the actor is actually operating in. And if you're somehow able to take this representative data and map that out into dimensional space, then good things start to happen. So first of all, you see that, again, this action doesn't happen locally, but it happens globally. So at any given point in time, it's local, But overall, it exists in the context of the dimensional world. And when you see that, then it becomes easier to understand what's actually going on. Okay? And once you have done that, then you can take also the motion of the actor, for example, the motion of the hands, and project that back against this reconstruction of the world you have performed. And now this makes more sense, because now you see what the hands are actually doing in the world, as opposed to see that from the perspective of the actor. So you go from this egocentric perspective, exocentric perspective, where things can make more sense. Okay, so that's my motivation for trying to bring back 3D into computer vision into sort of foundational sense. But now, how do we do that in practice? This is actually a very simple message, but I think it's very important. So if you want to move towards foundational 3D vision for AI, this has got to be a neural network. Okay. Why is that? Because neural networks are the language on which we are building AI. All right. This is completely obvious, maybe, but it's not so obvious if you do 3D computer vision. All right. So we have a neural network, and what do we want this network to be or to do? So we want this to have 3D capabilities. For example, we may want to put some images into the network as inputs, maybe one, maybe more. And then somehow, as outputs, the network should be able to provide a three-dimensional interpretation of this data. For example, three-dimensional reconstruction. Okay? And you want this network to have several properties for this to be actually useful. So it has to be general. It means that it has to work ideally with any input image you can put in, say any image you download from the internet. It has to be seamless. So it's got to be a neural network, and ideally it has to use standard components. So when you give this to another user of AI that is not a computer vision expert, or maybe not a 3D computer vision expert in particular, then they can build on this model very easily. So having a seamless system is extremely important for this to be a foundation. And it has to be practical. What do I mean by practical? It has to be efficient, and it has to work well, and solve all the interesting 3D computer vision tasks. So now if you look at how this 3D computer vision is done traditionally, you start with a bunch of images. Then there is a sum log, there's some operator there that does some sort of pairwise analysis of the content of those images. For example, is establishing pinpoint-wise correspondences between the images. Once you have that, then there is another block there, which takes those correspondences and translates that, or recovers from that, a three-dimensional interpretation of the data. And that usually is called structure promotion, boundary adjustments, maybe multi-view stereo, if you have the camera given to you. Now, this can be more general than that. It's not just about correspondences. You can have other types of pairwise analysis. For example, you can get depth maps, maybe you can get pairwise cameras. By the end of the day, the output of that is going to be fed into a system that performs some sort of optimization to give you the final answer, which is interpretation of the data in 3D. Now, my point here is that these are two different worlds. On the left, what you have are essentially either a handcrafted system, or more realistically now, learned system, deep networks, that solve stuff like image matching, depth estimation, maybe pairwise camera estimation, point mapping. And to the right, what you get is optimization, which is rooted in visual geometry, okay? And somehow that is iteratively, so it's an iterative solver that tries to solve a bunch of equations which are based on the inputs that you get from the deep networks. And these two words, you can combine them, but it's actually clunky. You can do it, but it's difficult. It's not ideal if you want a foundation of 3D, so the vision that is in 3D. What I want to do instead is to have geometry in one go. What I mean by that is I want to have a bunch of images as input. I want to have a big network there, maybe just a transformer, and as output, without any optimization ideally, I want to get all the 3D quantities of interest. Point-wise reconstruction, depth maps, correspondences, everything. Okay? So this is the model we have recently introduced, this first step, which is trying to achieve that, which is called VGGT. This is a play on word on the name of our group in Oxford, which is the VGG. Probably you know about it because of VGG very deep, which is a deep neural network, which actually is not 3D. And so I wanted to bring back geometry, individual geometry. So VGG stands for Visual Geometry Grounded, and then T stands for Transformer, and that's exactly what it is. So we start with a bunch of images. We compose them into patches, as I explained before, put that into a feature extractor, which is called Dyno. This become tokens. Then you add a random initialized token for each camera that's going to be used to estimate the camera parameters. And then you feed this into a big transformer. The transformer has a little bit of structure that I don't want to discuss today, but basically, fundamentally, it's just a big transformer. Then you recover your token after processing your network, and you're going to recover the camera tokens, and then the tokens that correspond densely to the image patches. And from that, you're going to get all the quantities you want. You're going to get the camerons at the top, you're going to get depth maps, you're going to get point maps to give the construction of the scene, and then we're also going to get features that we can use for point tracking. Okay, that's what we want to do, and we want just to propose this as a 3D foundation. So this is the sort of thing this model can do. So you can take 32 views of it like that, and in half a second you can get a nice 3D construction like so. This works with a range of a number of images as input. You can take 64 views, say, and then you get a reconstruction like this. Right. 128 views also works. And these are things that maybe you would be able to do with traditional systems. But what you cannot do with traditional system is something like this. So you get two images which have no overlaps at all. Now somehow, because the system is learned, has priors on what these things look like in 3D, you can still give you a three-dimensional reconstruction of these two images without having any explicit correspondence between the two. Okay? And in fact, the system, which is trained always with two or more images, actually at test time generalizes to the case in which you have a single image as input. So even if you have a single image in half a second, you can get sort of pretty reasonable 3D reconstruction of the bits of the scene you actually see. Okay? The next slide is slightly more boring. It's about numbers, but I think this is also important to convey the message here. So this is compared, VGT compared against traditional systems that use or not deep learning, but on top of that, they have bundle adjustment, which is a form of optimization. Then we have other networks that do 3D vision without bundle adjustments. This is more in the spirit of our model, and this is our model here. So you can see that what is important here is that this is not just the best model, but especially that it improves on top of methods that actually use bundle adjustment without using it. So even without optimization, this network, just a transformer, does outperform, at least in these experiments, methods that actually do use optimization. And if you add optimization on top, then you can do a little better still. All right? So it's not that the model transformer does perfect, it's not perfect, still improvable with optimization, but even the baseline is better, the one you could do with optimization before. This model is also fast. If you compare it with prior work, then it's fast as a model which is called faster, which I suppose suggests it's fast model. Okay? Here it is, and if you add bundle adjustment, it is slower for sure, but it's not as slow as previous work that actually used that. And the reason is that the network lends to a very good initial point, optimizing on top of which is actually easy. Now, this model is supposed to be a foundation. It has to be good for several different tasks. For example, here we use it for 2D matching. The model is not trained explicitly for matching, but it turns out that if you compare it against networks just specialized for image matching, it actually performs better than all of them. Same model, okay? And in fact, it turns out that this does very well on a number of tasks. So we have camera prediction, point band prediction, multi-view stereo, molecular depth estimation, 2D matching, and 2D tracking. So you can use the features also for the form of the tracking. In all cases, you're going to get these results which are either state-of-the-art or close to state-of-the-art, often with also relaxing some assumptions when you get these results. So this is a good model, essentially. And that's why I think this can be a good direction for building foundation for 3D vision. Now, this is not to say that the journey is finished. So this model is powerful. It can process from 1 to 300 images in one go, but it cannot process 1 million images. So if you want to reconstruct a big city and you have thousands of images, then it's not enough to have a network that does it. This is still beyond what we can do. And there are some other limitations. So in fact, as I showed before, you can still improve on top of this model if you have a bundle adjustment. So the journey is not ended yet. But still, this is good progress. This is a demo you can play with this model yourself. And this is me yesterday. Oops. Trying it out. This playing? Yes, okay. This is me playing with this model yesterday and trying to reconstruct the area around. Of course, it wasn't me flying to the building. I just downloaded the video of a drone. That's someone else did. Okay, so this is good, but this is a static model. The work, though, is dynamic. So the next part of the talk, we would like to discuss how we can try to take this and extend this towards building a 4D-dimensional representation of the work. So what is a 4D representation for me? So it's a way for a machine to express, to interpret data, which is not just static, but is dynamic. So for example, we want to establish matching our image points, which are not just static, attached to the scene, but also moving around. You want to reconstruct those points. You want to reconstruct not just the cameras, but also the motion within the scene. This is actually very important. If you want to get a 4D model, it means not just reconstructing 3D frame by frame, but also means interpreting or recovering the motion in 4D. So to do 2D plus time. Okay? And if you look at a part of a representation which was recently proposed as a way for deep network to do 3D interpretation of images called a point map. This was introduced by Duster, or popularized by Duster last year. It's a very simple concept. So what you do is take an image, and then at each pixel you attach the corresponding 3D point. Okay, that's it. Now, when this becomes interesting is when you have two images. So you extract 2 point maps from image 1, image 2, and the key there is that these point maps are viewpoint invariant. What do we mean by that? I mean that they both reconstructed with reference to the same 3D reference frame. So now if you overlap them like that, then you see that they coincide. Okay? I'm gonna do a little bit of math, just a little bit, just to show you what this actually means. So you're gonna add some symbols there. So you're gonna call an image I, viewpoint pi, the point maps P. Zooming here, all right? For the image 1, image 2, pi 1, pi 2 are the 2D points. Then we have P2 there, which is the point map. So the index there, 2, means that the points are extracted from the second image. The viewpoint, though, comes from the first image. So this is where you get this sort of crossing information between these 2 data points. And if you do that, then you get this viewpoint invariance. Now, why is this good? Well, for example, this allows you to find 2D correspondences. So if you have these 2 points on the red yellow cube, which of course you understand that they correspond, well, all you need to do to verify that is to evaluate the point maps and correspondences of U1 and U2. And because of viewpoint invariance, they will have to be the same 2D point. So you can check. It's a test. Tells you that these points are in correspondence. Okay? Now, if you pay attention, there was a problem here. Did you spot it? What is the problem with this? Some points are not static in both viewpoints. So if you look at this very carefully, you'll see that one of the two objects, the cylinder, is actually moving around, right? It's not static. It means it's moving in the world, it's falling down in this case, okay? So if you play the same trick, so if you compute your point maps and correspondences of points in the cylinder, well, this correspondence breaks because the point invariance is not enough, right? So what you can do, though, is you can try to modify the point maps to try to restore this invariance by counting for time. So what we do here is we estimate from each image not 1 point map, but 2, and we do that with respect to two different time references that we have because we have 3 images, all right? So let me zoom in again using equations. We have I1, pi1, I2, pi2 as before, but now we have also 2 times which are different because things move over time, okay? And then we extract 2 point maps like before. Both point maps, the pixels, the 3 points come from the pixel image I2. The point comes from the first image like before. And now the times, you see that one time comes from the first image and the other times come from the second image. That's it. If you do that, you can restore invariance. For example, here, if you fix the time to be the time of the first image, you see that now also the points in the cylinder coincide because we have removed time, or we have killed the variability with respect to time. Okay? And the other game you can play is if you take the point maps you get from the first image, you change time, then what you can recover very easily are time correspondences. You can reconstruct the motion in 3D, which is also very important. So this is here in action. This is not yet in the foundation model. This is an experience we did in Oxford, so the mass model is tail. But you can already see that you can convincingly reconstruct into these scenes where there are things that move, in this case the train. Okay? But what is important is not just that we can reconstruct into these things that move around, but we can also recover the motion. So what you see here to the left is by highlighting the heat map, the bit of the scene which is moving independently of the background, because there is something that is acting on the world, like yourself in this case, right? And in the middle, what you see is that there are these very thin lines. They're a bit hard to see, but these are tracked that we're recovering because of these dual point maps that recover also time. All right, so we can track the motion of the object in 3D. And once we have done that, for example, we can fit a cube into 3D to track the motion. Now the message here is, again, when you do this, then good things happen. And the good thing that happened in this case is that you can recover this sort of scene motion much better than if you do not have this sort of representation. So this is compared against Monster, which is a successor of Duster that is designed to do dynamics. but actually can only do that if combined with a 2D optical flow method. And because we're estimating everything from 3D directly, including the motion, then we can recover this sort of motion much, much better. Okay? All right. So this is what I wanted to say about reconstruction. I want to spend the last 5 minutes or so of my presentation discussing something else altogether. So in order to build a foundation model, it's fine to have an entity that can do interpretation of data in 3D, but what if you do not have any images input, right? So what if you want to conceptualize the dimensional world without having an image right now to look at? So this leads to the other problem, which is 3D generation. So suppose that I come up with a thought, like a body made of metal. So a body is a type of dog, of course, it's made of metal. And as a human, I can imagine what this would look like. So now what I want to do is to build a machine, a model, that is able to do the same. So it's able to generate a model of this object just by thinking about it or imagining it. So we've been working on this problem for a few years now. So this is an example from Meta 3D Gen, which was introduced last year. This is about texturing the object. So you see here a little model of a butterfly. Then we can prompt the machine saying something like a majestic monarch butterfly, and the machine can somehow paint the texture of the object. It's not just that, you can also conceptualize the objects in 3D directly. So you can come up with some prompts, and then you can imagine not just the texture, but also the three-dimensional shape of the objects, and then you can generate this content, which could be useful for example, video games or maybe special effects. Now, this is not the best model we have, so we're working now on a much better version of this, but we're not ready to share it yet. So this is last year, but this year, this will even work better. But what I wanted to tell you is a bit of the work we're doing around this to go beyond just objects. So first of all, how do we approach this problem? So one challenge here is that we want to conceptualize or translate a sentence into the object. This is difficult to do because to learn about this, you need a very large data set, which is usually not available when you're thinking about 3D data. But you do have very large data sets to learn image generators, as everybody here is well aware. So we piggyback effectively on the power of image generators to conceptualize these thoughts into an object. So we start with image generators. We say a bear in an armor, and then with this we can generate an image of that. And we modify the model to generate not just a single image, but multiple views of it. So because these views are consistent, 3D consistent, you can think that this multi-view generator that we fine-tune is now capturing a 3D pie around the world. Once you have done that, it's actually relatively easy to take these images and reconstruct the object into 3D like so. So this is the base technology. And let's see how we can extend that to something more interesting than just reconstructing an object. So I want to go in two directions. I want to go into the micro direction, reconstructing object parts, and then to the macro direction, reconstructing words. So for parts, so if you think about it, when you look at an object and you want to reason about its structure, it's not enough to think about that as a monolithic entity. You want to know that it's made up of different components. So here we have the object, which is a sort of panda bear king, and you want to know that it's composed of a crown, clothes, and the panda itself. So how do we do this? So the way we do that is we need to imagine, first of all, how we could decompose the object into different components. So for this, we again take our image generator and we task it with coloring the parts. And we color the parts in a way which is multi-view consistent. So now why do we do this with an image generator? Well, the reason is that part decomposition is ambiguous. So here we have three hypotheses, which are all equally good in how we could decompose that scene into components. There is no preference in how you do that. So you need to model this ambiguity, if you like, and that's what these generator models actually do that, model the ambiguity. So we do this. And once you're done your decomposition, then you have a bunch of parts which are not visually complete because there are self-occlusion. So here, for example, you see the street which is under the building. Once you have segmented it, it's not complete. So it's not possible from those images there to use them as a basis for the reconstruction without incurring some problems. What we do, again, we use an image generator to take those that partial information and complete. And why an image generator? Again, because the way you do this completion is ambiguous. So there are different ways of decomposing an object, reconstructing an object in different parts. This actually works very well. So now we're able to take those different concepts, like for example the burger, and we know that now that's made up of the bread, the tomato, the meat, and the cheese, right? And all these things are conceptualized or rationalized in 3D. And for the final bit, something fun. So I explained to you how we can go micro. Now let's go macro instead. So suppose we want to do word generation. So this has been something that's become popular this year. So this is a video animation from Word Labs, which is a startup in America that showed this a few months ago. That was very impressive. So you can go from that single image into reconstructing this little three-dimensional word. But you see there is a problem there. So you cannot walk very far away from where you start. The word finishes immediately. So what we wanted to do here is what is something like similar, starting from text, then being able to navigate around the word essentially in an indefinite manner. And we want to be able to do that from any prompt you like. And we want to cover a huge variety of different possible words. And again, this is a piece of work we didn't do in Meta, we did it in Oxford. So again, small resources, but we're still able to do it, which I think is interesting, by using models that the community has made available, just using them in a sort of innovative way. So how can we use an off-the-shelf 3D generator to create a word? So that's what I want to tell you about in just 1 minute. So that's what we do it, how we do it. So we essentially play SimCity, which is an old school video game in which you build a word out of blocks. So we decompose the word into blocks, we prompt them with text using an LLM, and then each block we reconstruct as if it was an object. It's not an object, but we can pretend it is because it's small enough. And then we can combine these different tiles into a word. And again, this is using just off-the-shelf components and done some clever prompting, if you like. So we start from a user prompt, say, a university campus, and then we use a language model, a text-to-image model, and an image-to-3D model to generate our three-dimensional word. And again, these are off-the-shelf components. All we do is to prompt them cleverly. I don't really have the time to discuss the details, but just to give you an idea of the sort of things you can do. Suppose you want to create a temple here. So you can use Flux, which is a state-of-the-art image generator, say temple, and off you get with an image of a temple. But this is not like a tile. It's not a good component for a word because it contains a background, contains some stuff that is not suitable for reconstructing a little chunk of the word. So what we do is we take Flux and we prompt it in a way that encourages that to give us an image of a tile. And the way we do it is actually extremely simple, but extremely clever. I think this is my student that came up with this. I guess he's the prompting master. What he did is, okay, let's just literally draw the base of the tile as an RGB image. Then ask Flux to paint what goes on top of that tile. Okay, that's it. If you put this information into Flux and you run it in painting mode, then it's going to create an output which looks like a tile, and that can be the basis for building a word. Without any training, there's no training here. That is to say the model is pre-trained and just off the shelf. Once you have that tile, then you can put that into, again, off-the-shelf model for image 3D, and you're going to get your tile model out. And then you can compose those things, and you get this fun little word to look at as a first starting point. I think this is great. It shows the variety of things you can do with relatively simple means using off-the-shelf building blocks. All right, so that's what I wanted to tell you about our research towards building a 3D foundation. Of course, this is just a snapshot of a much bigger and diverse portfolio of work we are doing. In particular, I wanted to focus on two different topics here. One was 3D analysis, if you like. So building these foundation models that can take one or more images of the word, and internally, we don't know whether the model is 3D or not, but you know that has a 3D understanding because it can give you a very explicit and very accurate 3D interpretation of the data. So internally, it's just a big network, just a big transformer, but you know that it's 3D capable because it's very easy to extract the 3D information from it. And then the other side, 3D generation. So when you do not have an image to start with, you still want to be able to reason about the word in 3D. And generation, these 3D products are fundamental for it. Now the community is progressing very, very rapidly into building these models. Objects are the starting points, but now we can do parts and we can do words, and the community is building from there. And I guess the sky's the limit. So thank you very much.